All right, so two things I want to do today, at least. The first is to start you on the homework for chapter 6, which is pretty easy, and in fact, it ought to remind you of things we kind of have seen, but nevertheless, I will start you on it. And then I am going to return to the ideas about convex analysis that I was presenting on Tuesday, and hopefully culminate to the point of being able to explain to you how convex analysis, the separation of convex sets, leads us to be able to solve a maximization problem with inequality constraints, even if the objective function is not differentiable. We've been doing it, but we've been doing it sort of, let's say, unofficially. We're saying, okay, if you have Leontief, then you're going to be forced to the corner. Okay, fine, that's one way to solve it, right? But then, what is the theorem that tells you, well, a tangent of sorts will exist that will separate the upper contour set of the objective function from the constraint? Visually, it is so entirely obvious once you get the idea that then if you ever want to read the saddle point characterization of the Kuhn-Tucker theorem proof, then that picture will just get you 95% there conceptually. So that's my aim. So problem 6.1, just to be really practical and start with what you wanted to talk about off the beginning, from the beginning, gives you the following function. Minimum, that's the one, right? Yes. All right. So then it wants us to find the conditional factor demands and the production function, essentially. All right. So, can we take derivatives? We would like to, right? We would like to take derivatives with respect to W1 and W2, but it's a bit of a problem because, of course, the minimum function is not differentiable exactly at the point of interest where W1 equals with W2. Okay, good, still recording. What are we going to do? One way to deal with it is to look at, break up the domain of definition of the cost function with respect to the W's in two parts, actually three parts. So, I'm going to view it this way, and then I will take derivatives in the parts of the domain in which the function is differentiable. So, start with the part of the domain where W1 is less than W2, right? If we start here, then the cost function simply becomes W1y, right? Okay, so Shepard's lemma, it says, to find the conditional factor demand for x1, differentiate this with respect to W1, so we would have that x1 is the partial with respect to W1 of the function W1y, right? Which of course is y. And don't worry that the Shepard's lemma does apply, even though I'm doing it bit by bit. And the reason it applies is that it is in fact derived from convex sets, and at the end of the day, it can easily be generalized with superdifferential, so it doesn't require differentiability. But meanwhile, let's just proceed this way. It's pretty practical and fairly obvious, I hope, right? So the x2, analogously, is going to be zero, of course, because there is no W2 to differentiate, right? It's gone away. Okay, so you do that. Then You do the other side, then you do this. And in this one, you kind of know that it doesn't really matter how much you want of one or the other factor, right? Because you're totally indifferent. Any amount between 0 and y is appropriate for factor 1, and the rest of it will be from factor 2. So that's really it for this. Once you have these, then you have to think, okay, what sort of production function do I have? Right? Because he asks about that as well. Well, one thing that we can already say, we've seen this. This kind of behavior, corner solutions, comes with perfect substitutes, right? And in particular, when I said when W1 equals W2, use any proportion of factor 1 and factor 2 as long as the sum is equal to y, so you can produce y. So they are perfect substitutes, right? So the production function is x1 plus x2. I have another marker that's even better, so let's read that.
So
yeah,
in the case, okay, so we are allowed, allowed when we see something like a minimum or like a maximum function, we are allowed to break it down and then apply Shepard's lemma or like do derivatives and everything with that.
Yes, but explicitly, what mathematically what happens is that I defined 3 different functions.
Okay.
Because I changed the domain of definition of my cost function, right? Now, on the domain where W1 is less than W2 and y can be any positive real number, that function is differentiable.
Okay.
And in fact, it is this function, right? Okay. So I have no qualms about taking derivatives, and so on, right?
Right.
Now, pedantically speaking, which is the only way to speak if you're a mathematician, I did not differentiate the original function.
Right.
Right? Mm-hmm. And when I reach this point here, I really have limited the domain of the function to just a line under the W subspace.
Okay.
Right?
Right. Okay.
Okay. And notice I attempted to make it all as an economic argument. I limited the technicalities of math here on purpose. But I tried to do it correctly. So in other words, I do want you to remember to be very careful taking derivatives when the minimum or the maximum thing appears in the definition of the function. Okay? Anything else on this one? Okay. So this is pretty much 80% done now for you, if not 90. So let me do 6.2 or start here. And by the way, let me ask, so has everybody started on the practice problems for the midterm? Okay.
I've started thinking about them.
Good.
Further than I have.
There is.
I know. Yeah. Well, you have another exam on Tuesday, so you can think about that at the moment. Okay. 6.2. Okay. 6.2 is pretty similar, but now I forgot the formulation. Okay. The cost function is this. Yeah? Question? You're okay? All right. This cost function is perfectly differentiable, no problem whatsoever. I don't have to futz around with dividing the domain in parts and whatnot. So I will apply Shepard's lemma immediately. So, for the demands, by the way, in the previous one, once you do the various subdomains, you want to write the demand functions for the x1, let's say x1, as 3 parts, right? For W1 less than W2, it is this. For W1 equal to W2, it is that. For W1 bigger than W2, it is this. Right? Okay. So now here, what we have is the partial derivative of the cost function. Which is of course what? Just y, am I right? And in fact, in this case, it is also x2, which is the partial of this same function with respect to w2, but they appear completely symmetrically, right? So from this one, we get that the conditional demand functions are always equal. Now you know what production function will give you this. Perfect complement, right? No matter what the price ratio of factors is, you always buy the same amount of each of the two factors. So the production function is Leontief, minimum of x1, x2, right? And again, I emphasize the economics of it rather than, proving it. But that's pretty close to an actual proof, actually. Because, how else would you never substitute what other production function exists? None, actually. Okay, with our usual assumptions. Okay, everybody okay with this one? Okay, and 6.3, that's even shorter. They tell us the cost function is W1 to the A, W2 to the B times Y. What do we know about A and B is the question. Okay? All right. What are the properties of a cost function? It's not a rhetorical question. I want someone to tell me. Yes, Luke.
All right, I'm going to slaughter this, but...
Okay, just try your best.
It is homogeneous of degree 1.
Homogeneous of degree 1. In what?
Factor prices.
Mm-hmm.
And then it is non-decreasing and also in factor prices.
Yes.
It is continuous.
And
what's the last one? Oh no. Concave.
Yes, in factor prices.
In factor prices.
Okay, excellent. So, from the property that says the cost function is non-decreasing in the W's, we immediately see that A cannot be negative, right? And B cannot be negative. All right? Now, what else? Homogeneous of degree 1, right? In the W's. So, homogeneity here means that if I put T W1 and T W2 instead of W1 and W2 for some T positive, right? This ought to come out equal to the original expression. All right, so that is equal to that, right? Gather the T's. Right? Okay. Now you want this to be, for every positive T, you want this to be 1. Because we want it to be equal to that. Homogeneity of degree 1. But the degree of homogeneity is right here. So A plus B needs to be equal to 1. his answer key also says concave in both prices, right? So then A and B separately has to be, he claims A has to be less than 1 and B has to be less than 1. But to be honest, I'm not completely convinced. Well, yes,
Yeah.
do the Hessian. So from concavity, oh come on, such a big deal, such a big deal. All right, but that's a very small difference. We already know A is non-negative, B is non-negative. They sum up to 1. So all we're going to try to rule out from this is that A is actually equal to 1 or B is equal to 1, right? So check it out. I mean, actually, I think, let's see. I think it's still concave if A is equal to 1 or B is equal to 1. So I'm not completely convinced by his answer key, and I haven't looked at it actually. So do the Hessian and check it. Because the property is not that the cost function is strictly concave. It is that it is concave. So the Hessian could be semi-definite, negative semi-definite, and we're still okay with that property. Okay? So, but again, it's just a question of writing down the Hessian and checking whether it has the properties that make it semi-definite, negative semi-definite. Okay, so that is all I was going to say about these problems, which is already 90% of what you need. Question?
So for this one, where the reason you're saying you're skeptical of whether it could be whether
do we need the strict inequality? I'm not completely sure.
And is that because if one of them was 0 and if one of them was equal to 1, we have a linear cost function, which is still
right, but it's still
okay.
concave.
Okay.
Right.
Okay.
The property doesn't say.
Right.
Now, in economic terms, it would be an extremely weird thing, right? Because then in the cost, you would only have W1, for example, or W2.
Right.
Really? Why? How?
Yeah.
So figure it out. It's entirely possible he has something further in mind that I missed. But you have to do something for the homework. I'm not going to do all of it for you, so figure it out, okay? All right, so I'm switching gears. It's a good thing that there are only gears in my mind because I cannot drive a car that has manual transmission. In that case, switching gears would be pretty painful. Now, let me ask you this. Did you all see this document? Did everybody laugh at Pac-Man?
I got such a kick out of that. I was in the library in the quiet section. I had to
It wasn't that quiet after that, right?
Myself.
It's a perfect example of sets that cannot be separated. So, okay, so what I want to do is I want to kind of go over some of this, but I will not write everything that's already in the document, all right? And I will say one thing about, right, okay. So, one thing is a mistake. I put a sentence in the wrong place. So I'm saying it here on record. In the first paragraph, I have a definition of a hyperplane. All right? And then I said the vector P is the normal vector of the hyperplane. But the sentence that says it is orthogonal, perpendicular to the hyperplane, should have been right there because it refers to the vector. But for some reason, I typed it in the end of the next paragraph. So, okay? All right. So the ideas here are basically how do you get when do you get the chance to separate sets with hyperplanes, right? And the various separating hyperplane theorems give you exactly conditions that allow you to separate sets. Sufficient conditions. Okay? Why do I say sufficient conditions? It is possible that you have two non-convex sets that can be separated, right? So for two sets to be separated, it is not necessary for them to both be convex, right? But as Pacman illustrates, you cannot really count on the existence of a separating hyperplane if your sets are not convex, all right? So then we're looking for sufficient conditions to enable separation. All right. So the various pictures on the second page illustrate various kinds of separation. If you have the ability, if you have room to put a whole band between the sets, you know, the two discrete hyperplanes, one on the same, on one side of the other, right, parallel to each other, then this is a strong or strict separation, whatever he calls it, right? In most cases, we don't need that. In Econ, the basic thing we do is we want to be able to first separate a point from a set, and then a set from another set. Okay? Separating a point from a set is going to lead us to having a proper concept of tangency. And the 5 pages, whatever I put up on Canvas from the Maskoller, Weston, and Green book, talk about essentially finding all the tangents to a set, even if it's not convex, by convexifying it, find the convex whole, and then you proceed from there. That operation is exactly how Varian starts chapter 6. Remember, he has the set that has a hole in it, and then he fills it in. So, I am not going to go over the details of the Maskoller, Weston, and Green argument, but hopefully that makes you understand what is the filling operation and what the support function has to do to help us. Okay? One thing I will clarify from Maskoller, Weston, and Green is their figure. They have a set in panel B of figure 3F2, and it looks something like that. They call this set K, all right? And then they say, find all the hyperplanes, the half spaces, closed half spaces, that contain this set. Now, a closed half space, how do you find it? So here we are in R2, right? So how do I find half spaces? I define them in my document for you. You need a hyperplane, and everything on the hyperplane and one side of it is a half space. So for example, if I draw this hyperplane, then indeed, if I look at this half space that it defines, K is in it. It's a subset of it. But I could do better. I want to approximate K as much as possible. So I don't want this hyperplane, in fact, anyone even farther away. I want to go as close as possible to the set I'm approximating. So I'm going to be touching it, right? How do I know I can do that? Well, I don't know that I can do that. If it were convex, however, the theorem that says how you can separate the point on the boundary from the interior, that would work. I don't know that I included it, but I had to. The 4-page document I put up, that I put together with a Pacman and all that, that came as a distillation of several dozen pages in Kim Border's notes. So anyway, so I am telling you that if you have a convex set, and we'll ignore this gap, this gap here now. At the boundary, you always have a hyperplane that attaches and leaves the set completely on one side. Okay. Then the most interesting hyperplane is, of course, that one for this particular set, right? And so the set then is on this side of the hyperplane, right? So let me start shading those half spaces I'm talking about. So we're talking about this half space, that one, and so on, and so on, and so on. They have a few more, but they stop. Of course they stop, because there's no way to put an infinite number of half spaces here and still make sense. But at the end of the day, the picture may be misleading and they don't clarify, because they have something like one more here, one more there, and they have one more here. And what they shade is, and of course all of K, right? That is not the convex hull, because you need to take the infinite intersection of all such half spaces. And this is just a few of them. For example, consider this point here. Does it belong to the infinite intersection of all those half spaces? No, it doesn't, because it doesn't belong to that one. Right? For a point to be in the infinite intersection of sets, it needs, by the property of intersection, it needs to be in every one of the sets. Right? So in fact, the convex hull, the closed convex hull of this set, is the set itself with the addition of this area and that skin. That's it. Nothing outside on this side, the convex side. Okay? All right, so I wanted to clarify that. Now, I want to talk about two versions of the Minkowski. It's probably Minkowski, but Polish. You can tell me something about Ukrainian and Russian, right? But not Polish.
No Polish.
There is a famous lemma in topology that I have no idea if I'm saying correctly. The Knaster, Kuratowski, and Mazurkiewicz lemma. That's a mouthful right there.
Rolled off the tongue.
Absolutely, for Polish people it does. This one is Minkowski. Americans say Minkowski. How do I know? I know Greek and English, that's it. And math. All right. So, the first version of the separating theorem says, let S and T be to disjoint convex sets. If they're disjoint, you don't have to say anything about their interiors. It says there is a vector that will separate them, that will be perpendicular to a hyperplane that separates them. Now, if they're like this, S, T, then it's pretty obvious. Plenty of solutions. But also, I had an example to show you the need for the interior of one of the sets to be on empty. That doesn't apply here. Right? For example, what was my example? Do you remember? The two axes? Mm-hmm. And I said, oh, you can't separate those, but they're convex sets. What's the problem? Well, they don't have non-empty interior. This does not bother this version of the theorem, because the two axes intersect. So they violate the assumption that they are disjoint, right? So the only way you could have two lines and apply the theorem to them is if they are parallel to each other, in which case they're obviously easy to separate. So that's one version of the theorem, but it is slightly less exciting than what we need for example, for maximization under constraint. Because there we want our sets to be touching, right? Unless we take the interior of the upper contour set. So let me now switch to making a picture of maximization under constraint. I will not make things differentiable. And then, okay, we'll take it from there. So suppose I have easiest way to make a non-differentiable objective function and constraint set is to build the constraints out of, for example, two linear functions or more. So then, suppose this is the constraint set, the feasible set. Okay? These two lines hyperplanes represent constraints. A good example, and it is, if you remember the thing about maximization, Kuhn-Tucker, that Sudong found and put on Canvas, it has the actual example that motivates this, which is wartime rationing. At times of war, when governments wanted to reduce the civilian consumption of certain items so they can send more resources to military production, they introduced ration coupons. So it wasn't enough now, if you wanted to buy a loaf of bread, it wasn't enough to bring money to pay for the bread, but you also had to bring a ration coupon that says you're entitled to a loaf of bread. So you had two constraints, your regular budget constraint and your budget constraint for coupons, right? And depending on how many coupons per loaf of bread versus butter on the other axis you had, and what were the prices in dollars of the two goods, these two budget lines would be different, but both need to be satisfied. Okay? Okay. Now suppose that over here is the upper contour set of your, say, utility function, whatever it is you're maximizing, in other words. Right? Now, what have I done here? I have created a feasible set out of the intersection of four half spaces. Four? Well, non-negativity is in the picture, even though I did not, until now, mention it by name. So one constraint is x1 is, x2 is non-negative. Right? The other is that x1 is non-negative. Then, this constraint has to be satisfied. Right? And then that one. So I have four half spaces, closed half spaces. They all intersect into a set that is bounded by these points, and then the line segments connecting them. Okay? The circles I wrote are just to highlight those points. They're not part of anything really. Okay? All right, so this is your feasible set. Okay? And observe, it is the intersection of a bunch of convex sets. In this particular case, it's a bunch of half spaces. Furthermore, they're all closed sets. They contain a boundary. Right? So the intersection here is closed and convex. And in fact, given the nature of the hyperplanes, it's also bounded. So we don't have to worry about the existence of a maximum. It will be there as long as the objective function is continuous. Yeah.
Did you say all of the half spaces are closed?
Yes, because all the constraints are less than or equal to.
Okay.
Right? So
I'm just having trouble seeing how like the x2 half space is a closed space. If it's
because
if
it
it's
allows
x2
x2 to be 0. It says x2 greater than or equal to 0.
Okay.
Right? So
and then it's bounded from the line.
Right.
Okay.
The intersection of all four is bounded.
Oh. Okay,
Each half space, of course, is not bounded.
Okay, that's where I was
Okay. All right.
Thank you. Yeah, that makes sense.
And it's because of the construction that this particular is bounded. I'm not saying that if you take four half spaces, their intersection automatically will be bounded.
Right.
No. But it will be convex and it will be closed.
Right.
But given this kind of configuration, it is clearly bounded, which wasn't really my point, but it's worth pointing out. As long as my objective function is continuous, I will have a maximum. Okay, so I've actually drawn the maximum. Here is an upper contour set, weak upper contour set of what it is that I am maximizing. All right? So the maximum is here. So in the standard way we define the Lagrange multipliers. The first time you saw them in calculus, for example, they come in from derivatives, right? And they're motivated by means of derivatives as prices and whatever, right? What I'm trying to explain here is that, in fact, if you have that the upper contour sets of the objective function are convex sets, so the objective function is quasi-concave, and the physical set is a convex set, and the maximum exists, you do not need differentiability anywhere to find Lagrange multipliers. They will be the components of any of the normal vector of any hyperplane that separates the what? Separates the strict upper contour set from the feasible set. Because then you couldn't have done better. Because the moment you attempt to do better, you enter the strict upper contour set, which is the interior of the weak upper contour set, and now you really cannot afford it. You're outside this set. Because the sets are separated by Minkowski's theorem. So Minkowski's theorem is going to give you, actually in this case, a whole bunch of different possible hyperplanes that separate, right? And so the normal vectors of these are going to give you the Lagrange multipliers. And you have here, in fact, an embarrassment of riches. There's lots of different Lagrange multipliers that will do the job. Because exactly the maximum happened to be right at the place where both the feasible set's boundary and the level set touching it are not differentiable there. If one of them were differentiable, then the Lagrange multipliers would be unique. So let me give you a picture of that. And then I will finish by telling you what is the super differential and how it has anything to do with this. Okay? Any questions about this? Okay. So what if I draw the exact same picture, but use a different objective function? I'm going to leave this up here so you can compare. All right, so something like this, like that. Well, so much for making it look quite a bit the same. Really not good at this. Okay. Let's accept that this picture is the same as that in terms of the constraint. All right? So let's highlight the constraint in green as before. But now suppose that the maximum is, for example, here, because the upper contour set of the objective function hits the constraint not right at the corner, but just on one of the facets of this. This is called the polyhedron. It's an intersection of half spaces. And so it has vertices and it has facets. The terminology here is pretty straightforward. Okay. Everything I said before applies to this. There will be a separating hyperplane that separates the strict upper contour set, the interior of this, from the constraint set. But we don't have a lot of freedom. In fact, we have no freedom in choosing this hyperplane. It's dictated by the slope of this constraint, which is the one that is the only binding constraint. Because around this point, where it happened, the intersection happens, well, the tangency happens, the function describing the constraint locally is in fact linear and therefore differentiable. And that will force you to have to use that line, right, as the separating hyperplane and no other. Whereas here, with the two kinks falling on top of each other, we had plenty of room to choose this, our hyperplane. Okay? Similarly, if I had the same picture again, but my objective function had a smooth level set at the optimum, then I would be seeing this as the interior of my upper contour, so the strict upper contour set. And because the indifference curve here is smooth, it only has one tangent here, so that will force my hand in the choice of the separating hyperplane, and therefore the Lagrange multipliers. When we do general equilibrium, without proving the details, I will use a picture like this to show you the existence of equilibrium if we have a Pareto efficient allocation to begin with. It's the second welfare theorem. And there you will see that it's the same picture, that here it gives us Lagrange multipliers and there it gives us prices. So the connection between Lagrange multipliers and prices is very deep. And Leonid Kantorovich, who got the Nobel Prize early on, won it because of seeing deep into those problems and seeing the importance of the Lagrange multipliers as prices. Questions? Okay, and now a few words about superdifferentials to hopefully tie all this together and generalize it a little bit, and then we are done. Okay. Okay, so if you have a concave function, I'll say the whole thing in terms of concave functions only. Obviously, if you have a convex function, flip everything upside down and the same thing applies, okay? So if you have a concave function, what do we know about its definition? Well, there's a number of ways to define it. We have the formal definition with the t and the x1 and the x2, tx1 plus 1 minus t times x2 and so on. But that also translates to the one definition that makes convex analysis completely applicable here, which was, give me the function and find its subgraph, or the notes that I was reading to create this stuff for you guys the other day, call it the hypograph, because for a convex function, nobody says supergraph, but they say epigraph. So Kim Border is pedantic enough, so he outranks me on this. He said, well, if epigraph comes from the Greek, both components of the word, then subgraph should not be used because sub is from Latin, so hypograph. Now everybody calls this a subgraph, so I'm going to stick with that. Everybody except Kim Border, of course. Incidentally, Kim Border on his website has a wonderful collection of very extensive notes on math and so on that he's been using to teach at Caltech for decades. So for those of you who will go and get a PhD, he has some really good in a place that demands much more math than here. Those are wonderful for review for prelims and stuff like that. If you master them here, then you're gonna fly through prelims. They're a little, they're pedantic, so everything is there, everything is proved, mostly. So, but they're really, really good. I don't have the time to go to do all that, and I'm not teaching you the math class, even though it may appear that I am right now. So let me just then tell you, if a function is concave, its subgraph is a convex set. That is, in fact, a way to define it. All right? So a concave function, a function is a concave function if and only if its subgraph is a convex set. If and only if. Okay. Well, take a point on the graph of the function. Because of the convexity of the subgraph, the hypograph, and because of the theorem that we know now about separating a point from a set, we know that we can separate the set containing this point. A set containing a single point is a convex set, right? You cannot have holes in it. There is only one point. So separate that from the set that of the strict subgraph, strictly below the graph. Well, then the separation theorem will tell you, yeah, there is a hyperplane that does that. Right? And now you see the other stuff that you learned in first calculus. When you heard about the concave function, one of the ways to characterize it is, hey, take the tangent to the graph at any point. The function is always below the graph, never above it. It could actually coincide with the graph if it's a linear function, for example. Okay? Now, in this picture, the convexity of the subgraph, yes, gave us the hyperplane, the tangent hyperplane, but it was not not telling us anything new, because this is a differentiable function the way I drew it. And all I needed to do was, you would say, just take the derivative there, and then you know the tangent. Okay, so convexity does that when the function is differentiable, but it also does it when the function isn't. here's a function. Here is its subgraph. Is that subgraph a convex set? Sure it is, right? All right. And why is that? Because, of course, that's a concave function. All right. Now I ask, let's find tangent. Kick my water bottle and then find the tangent at that point. All right. Now I think you know what I'm going to do next. I'm going to argue that because of the separation theorem, I can separate. There will be a hyperplane, there exists one, in this case more than one, hyperplane, that separates this point from the subgraph, the strict subgraph of the function. Now I have lots of choices. Right? Like this, like that. In fact, the boundary of the choices is easily seen if I draw the normal vectors of all of these. So one extreme is I can take what would have been the derivative of the function from the right at that point, right? Which would be this. Same slope as that. Okay, that's one normal vector of a hyperplane that works. And then I can tilt it like that, like that, like that. And then I have this, and then that's another normal vector. And any one in between, that is vectors in this cone, are normal vectors to hyperplanes that are tangent to the graph of the function at that point. This is the basis of the superdifferential. The entire set of those normals, that cone, is called the superdifferential of the function. And then you get very cool results, like for example, the way I've drawn it, right? I have a maximum there. This just happened to be, I didn't actually plan it that way, but that's how intuitively I wanted to draw it. Then you would think, okay, if the function was differentiable at that point, then the tangent would be horizontal. And I ask you, among all of these that are tangents here according to this, is there a hyperplane that is horizontal? And the answer is obviously yes, because look, the vertical normal vector is part of this cone. So it remains true that if I enlarge my concept of tangent to allow for non-differentiable functions, and if my function is concave, then the derivative at a maximum will contain 0. Here the derivative is a set. It's a set of all the normal vectors of all of those supporting hyperplanes. Make sense? So we have a generalization of the concept of derivative and an idea of how then that can be used to come up with first order conditions and so on for maximization, just as long as we're maximizing a concave function. Because this stuff will go all weird if the function doesn't have to be concave. Concave functions have all sorts of other wonderful properties that I'm not going to talk much about. For example, in the interior of the domain of definition, every concave function has to be continuous and stuff like that. Any questions? All right. Stop this.